Hello everyone, my name is Yash Yadav and my enrollment number is DE240228. I am from International Institute of Professional Studies and the subject is Numerical Analysis and Design. This is my third assignment uh, and the assignment asks us to solve specific numerical problems and to write code, build iteration tables and etc. So let me go through each section with the complete solution. So the section 1 asks us to find the root of the polynomial f of x equals x squared minus x minus 1 equal to 0 using the 5 different methods. So before I begin, let me point out something beautiful about the equation. Its positive root is 1 plus the square root of 5 divided by 2, which equals approximately 1.6180. This is the famous golden ratio, the same ratio found in Nautilus shells, sunflower spirals, and etc. So all 5 of our methods will converge to the same value 1.61803 and dot dot dot. So before this I checked f of 1 equals 1 minus 1, which is minus 1, that is negative, and f of 2 equals 4 minus 2 minus 1, which is equal to 1, that is positive. So there is definitely a root in the interval from 1 to 2. So all bracket methods will use the same interval. Bisection method. Bisection method. Assumptions. F is continuous. F of 1 times of F2 is minus 1 times plus 1, which is negative. So a root exists between 1 2 by the intermediate value theorem. So I use tolerance epsilon equal to 0.001. The bisection formula is just the midpoint C equals A plus B divided by 2 and our iteration 0 where A equals 1, B equals 2, midpoint C equals 1.5 and f of 1.5 equals 2.25 minus 1.5 minus 1, which equals minus 0.25, that is negative. So our root is in 1.5 to 2 range. Okay, so we'll update A to 1.5. In iteration 1, A equals 1.5, B equals 2, C equals 1.75, and f of 1.75 equals plus 0.3125, that is positive root. So the root is in 1.5 to 1.75. We will update our b to 1.75. So the interval keeps halving by about iteration 11. We reach the root 1.6180 to 3 decimal places. So the error after n steps is at most b minus a divided by 2 to the n, which is 1 divided by 2 to the 11, about 0.0005. The Python code. So here we define f of x, set a to 1, b to 2, while the half interval is bigger than epsilon. Compute c equals a plus b over 2. If f of a times f of c is negative, set b to c, otherwise set a to c, and print the root. The time complexity O of log base 2 of b minus a over epsilon, about 11 iterations for epsilon 0.001. And our space complexity is O of 1, order of convergence p equals 1, meaning linear. Regula-Falsi method. Assumptions. Same sign conditions. F of 1 negative, f of 2 positive. F is not too flat near the root. The formula is C equals a minus f of a times b minus a divided by f of b minus f of a. This is the x coordinate where the straight chord from a comma f of a to b comma f of b crosses the x-axis. Our first step where a equals 1, f of a equals minus 1, b equals 2, f of b equals plus 1. So c equals 1 minus 1 times 1 divided by 1 minus minus 1, which equals 1, plus 0.5, which equals 1.5. So our f of 1.5 is minus 0.25, which is still negative. So a moves to 1.5. Here our key observation is that here b stays at 2 for every single iteration. It never moves. This is called one-sided convergence, a known limitation of Regula-Falsi. The method still converges just from one side only. By iteration 5, the root is 1.6175, which is very close to 1.6180. Here it converges faster than bisection for smooth functions because the chord is smarter than the midpoint. The time complexity O of n and the space complexity is of O of 1, and the order B is approximately 1 but superlinear in practice. Secant method. Assumptions. Two starting gases x0 equals 1.5 and x1 equals 2. Secant method. Assumptions. Two starting gases x0 equals 1.5 and x1 equals 2. No bracket needed. F is smooth near the root. No derivative is required. The formula is xn plus 1 equals xn minus f of xn times xn minus xn minus 1 divided by f of xn minus f of xn minus 1. So in iteration 1, x0 equals 1.5, x1 equals 2, and f of 1.5 equals minus 0.25. F of 2 equals 1, so x2 equals 2 minus 1 times 2 minus 1.5 divided by 1 minus 0.25, which equals 2 minus 0.5 over 1.25 equals 2 minus 0.4 equals 1.6. Let me recalculate. Okay, so 1 times 0.5 equals 0.5 divided by 1.25 equals 0.4. So x2 equals 2 minus 0.4 equals 1.6. Iteration 2, x1 equals 2, x2 equals 1.6667. Approximately after 4 iterations, the method converges to 1.618034, matching the golden ratio to 6 decimal places. So the order of convergence of secant method is 1.618, the golden ratio itself. This is famous mathematical coincidence. The method that finds the golden ratio converges at the rate of golden ratio. The time complexity is O of n, about 4 iterations for 6 decimal places, and the space complexity is O of 1. No derivative needed is the big practical advantage over Newton. Newton-Raphson method. Assumptions. F prime of x equals 2x minus 1 exists and is not 0 near the root. Initial guess x0 equals 2. Formula is xn plus 1 equals xn minus f of xn divided by f prime of xn. For our function x minus x squared minus x minus 1 divided by 2x minus 1, the iteration 0 equals where x equals 2, f of 2 equals 1, f prime of 2 equals 3, so our x1 equals 2 minus 1 over 3, which equals 1.6667. In iteration 1, our x equals 1.6667 and f equals 0.1111, f prime equals 2.3333. So x2 equals 1.6667 minus 0.1111 over 2.3333, which equals 1.6190. And in iteration 2, f is now about 0.001, which is very close to x3 equals 1.6180. In iteration 3, root to 10 decimal places. Okay, so 1.61803398887 done in 4 iterations. This is quadratic convergence in action. The number of correct decimal digits literally doubles each step from 1 to 2 to 4 to 8. The time complexity is O of n, just 4 iterations. Space complexity is O of 1, order p equals 2, and it is quadratic, the fastest among all these methods. Fixed point iteration. Assumptions. Here we rewrite x squared minus x minus 1 equals 0 as x equals g of x. I choose g of x equals square root of x plus 1. The contraction condition. Here g prime of x equals 1 divided by 2 times square root of x plus 1 at x equals 1.6. This is about 0.31, which is less than 1, so the iteration converges. Starting from x0 equals 1, x1 equals square root of 2 equals 1.4142, x2 equals square root of 2.4142 which equals 1.5538, x3 equals square root of 2.5538 which equals 1.5981. So by iteration 6 or 7 we reach 1.61803. The geometric picture, here we plot the diagonal y equals x and the curve y equals square root of x plus 1. Their intersection is the fixed point 1.618. Starting at 1 on the x-axis, we go up to the curve, then horizontally to the diagonal to read off the next x value. Then back up to the curve. This recreates a staircase that spirals inward toward the intersection. If I had chosen a different g of g, for example, g of x equals x squared minus 1, so the derivative at the root must be greater than 1, and the staircase would spiral outward, that is diverging. The choice of g is everything. The time complexity is O of n with linear convergence, and the space complexity is O of 1. Section 2, Interpolation. Okay. So in section 2, we have given 5 data points and asked us to estimate f of 9, a value which is not in the table, using the different interpolation methods. First, an important observation: the x values are 5, 7, 11, 13, 17. So the gaps are 2, 4, 2, 4. They are not equally spaced. So this matters enormously for which methods we can choose. Okay. First is Lagrange interpolation. Lagrange methods work for any spacing. So this is our primary approach. Formula P of t equals the sum over I of yi times Li of t. Each Li of t is the product over all j not equal to I of t minus xj divided by xi minus xj. I want to find P of 9. So there are 5 data points. So there are 5 basis functions L0 through L4. For L0 at t equals 9, the numerator is 9 minus 7, 9 minus 11, 9 minus 13, 9 minus 17, which equals 2 times minus 2 times minus 4 times minus 8. This is 2 times 2 is 4, times 4 is 16, times 8 is 128. But we have an odd number of negatives, 3. So the product is minus 128. And the denominator, that is 5 minus 7, 5 minus 11, 5 minus 13, 5 minus 17 equals minus 2 times minus 6 times minus 8 times minus 12. There are 4 negative, so multiply to positive. So 2 times 6 is 12, times 8 is 96, times 12 is 1152. So L0 of 9 equals minus 128 divided by 1152, which is minus 0.1111. Similarly for L1, L2, L3 and L4. So our final answer of f of 9 equals 150 times minus 0.1111 plus 392 times 0.53333 plus 1452 times 0.8889 plus 2366 times minus 0.3333 plus 5202 times 0.02222. So working this out, minus 16.67 plus 209.05 plus 1290.63 minus 788.67 plus 115.48, which equals approximately 810. So our f of 9 is approximately 810. So the time complexity is O of n squared and space complexity is O of n. Hermite interpolation. Hermite requires both function values and derivative value at each node. We only have function values, so we estimate the derivative using central differences from the data. For x equals 7, f prime of 7 is approximately f of 11 minus f of 5 divided by 11 minus 5, which equals 1452 minus 150 over 6 equals 217. Similarly, f prime of 11 is approximately 2366 minus 392 over 6 equals 329, and f prime of 13 is approximately 5202 minus 1452 over 6 equals 625. With these estimated derivatives, we use the doubled node divided difference algorithm. We create a new node array Z where each xi appears twice. The divided difference table is constructed with the derivative values filling in where two consecutive nodes are equal. The resulting Hermite polynomial h of 9 gives approximately 810, consistent with Lagrange since both interpolate through the same data. Hermite gives a smoother curve because it also matches the slope at every data point, not just the value. It is used in animation and computer graphics and etc. Divided difference table. The divided difference table is built as follows. The column 0 is just the y values 150, 392, 1452, 2366 and 5202. And our column 1 contains the first order divided difference. So between x equals 5 and x equals 7, it's 392 minus 150 divided by 7 minus 5. That is 242 over 2, which equals 121. Between x equals 7 and x equals 11, it is 1452 minus 392 divided by 11 minus 7, which equals 1060 over 4, which equals 265. Similarly, for between x equals 11 and x equals 30, where it is 2366 minus 1452 over 2, which equals 457. And between x equals 13 and x equals 17, it is 5202 minus 2366 over 4 equals 709.25. Column 2, we have second order difference, where 265 minus 121 over 11 minus 5 equals 24. 457 minus 265 equals 457 divided by 265 over 13 minus 7 equals 32, and continuing this gives the full table. The diagonal entries become the coefficients of Newton's divided difference polynomial. Evaluating this at t equals 9 gives the same answer, that is approximately 810. The O of the time complexity is O of n squared to build, and the space complexity is O of n squared. Okay, the evaluation O of n using Euler's method. Okay, forward and backward difference table. This is critical observation that the question requires us to address. Forward and backward difference tables requires the x values to be equally spaced, constant step h. Our data has gaps of 2, 4, 2, 4. These are not equal. Therefore, the forward and backward difference tables cannot be meaningful applied to the dataset. So my conclusion for these two subsections that they are not applicable to the dataset due to unequal spacing of x values, and the correct alternative is the divided difference method and Lagrange method, which handles any spacing. Section 3, numerical differentiation from data, which is this is given. Okay, so differentiation via interpolation. The interpolation based approach, we take our Lagrange polynomial p of x, which passes through all 5 points, and differentiate it analytically to get p prime of x. This gives an approximation of f prime of x. The derivative of each Lagrange basis function Li at a point t requires a summing product of t minus xk for all k not equal to both I and j, divided by the denominator product. For a simpler approach at the interior nodes, we can use the divided difference table. The second order divided difference approximates f double prime divided by 2 factorial, and the first order divided difference approximates f prime. The geometric interpretation, we have drawn a smooth degree 4 polynomial through the 5 data points. The derivatives we compute is the slope of that polynomial at each point. This approximates the slope of the true unknown function. However, for very large n or badly chosen nodes, The polynomial can oscillate wildly, so differentiation amplifies errors. Finite differentiation. Here, instead of building a complete interpolation polynomial, we directly estimate derivatives using nearby data points. Since our x values are not equally spaced, we cannot use the standard equal spacing difference tables directly. So we use divided difference based finite difference approximations. Now let's read the formula properly. For the forward difference formula, we say f dash of x is approximately equal to f of x plus h minus f of x divided by h. And for the central difference formula, f dash of x is approximately equal to f of x plus h minus f of x minus h divided by 2h. Now at x equals 5, we use the forward difference formula 392 minus 150 divided by 2, which gives 121. At x equals 7, we use the central difference formula where 1452 minus 150 divided by 6, which gives 217. Similarly, at x equals 11, 2366 minus 392 divided by 6, which gives 392. And at x equals 13, 5202 minus 1452 divided by 6, which gives 625. Finally, at the endpoint x equals 17, we use the backward difference formula 5202 minus 2366 divided by 4, which gives 709. Now for the second derivative, we use divided difference. The formula is f double dash at 11 is approximately equal to 2 times f bracket 7, comma 11, comma 13. And that gives us 81.5. At the bottom, you can also see the Python implementation where the code automatically chooses forward, backward, or central difference depending on the position of the point. Next, we move into numerical integration, also called numerical quadrature. The goal here is to approximate definite integrals numerically when solving them analytically becomes difficult. We will cover trapezoidal rule, Simpson's one-third rule, Simpson's 3/8 rule, Widal's rule, and Gauss quadrature. Newton-Cotes formula. The basic idea is simple. First, approximate the function using interpolation polynomials, and then integrate those polynomials exactly. The general Newton-Cotes formula is pronounced as integral from a to b of f of x dx is approximately equal to h times summation c I into f of xi, where h equals b minus a divided by n. Now for n equals 1, we get the trapezoidal rule. The formula is read as integral of f of x dx is approximately equal to h by 2 into y0 plus y1. For Simpson's one-third rule, integral is approximately equal to h by 3 into y0 plus 4y1 plus y2. For Simpson's 3/8 rule, integral is approximately equal to 3h by 8 into y0 plus uh, 3y2 plus y3. And finally for Widal's rule, 3h by 10 multiplied by 0 plus 5y plus y2 plus 6y3 plus y4 plus 5y5 plus y6. Now notice how the error order improves. Trapezoidal rule has error order O of h squared, while Simpson's rule improve to O of h power 4, and Widal's rule reaches O of h power 8. Gauss quadrature. Unlike Newton-Cotes method, this does not use equally spaced points. Instead, it selects optimal nodes and weights to maximize accuracy. The formula is pronounced as integral from minus 1 to 1 of f of t dt is approximately equal to summation of wi f of ti. And for transforming intervals, x equals b minus a divided by 2 into t plus a plus b divided by 2. One major advantage is, with n points, Gauss quadrature exactly integrates polynomials up to degree 2n minus 1. So with very few points, we can achieve extremely high accuracy. Section 5. Linear equations. Now we move to solving system of linear equations. We are given x plus 2y plus 3z equals 14, 3x plus 2y plus z equals 10, and 2x plus 3y plus 2z equals 14. And we will solve this using Gauss elimination, Jacobi iteration, and Gauss-Seidel methods. Gauss elimination with pivoting. First, let's look at the Gauss elimination with partial pivoting. The goal is to convert the matrix into upper triangular form. Before elimination, we perform pivoting, meanings we swap rows so the largest coefficient becomes the pivot element. After elimination, we use back substitution. For the final row, we calculate z equals 3, then substituting upward gives y equals 2 and x equals 1. At the bottom, NumPy verifies the same solution. Jacobi iteration. The rearranged equations are pronounced as x equals 10 minus 2y minus z divided by 3, y equals 14 minus 2x minus 2z divided by 3, z equals 14 minus x minus 2y divided by 3. In Jacobi method, every new value uses only old values from the previous iteration. Initially, the method diverges because the system is not diagonally dominant. After reordering the equation, the method converges properly, and after several iterations, we reach x equals 1, y equals 2, and z equals 3. Gauss-Seidel method. Gauss-Seidel method is similar to Jacobi's, but with one important difference. As soon as a new value is calculated, it is immediately reused in the same iteration. Because of this, convergence becomes much faster. With only 5 iterations, the value becomes extremely close to x equals 1, y equals 2, and z equals 3. Section number 6, which is approximation. Now we move into approximation methods instead of perfectly passing through every point. Approximation methods try to produce the best overall fit for the data. Least squares approximation. In least squares approximation, we minimize the total squared error. The error function is pronounced as E equals summation of yi minus p of xi whole squared. For a linear fit, p of x equals 0 plus a 1 x. Then we differentiate the error with respect to the coefficient and set them equal to 0. These equations are called normal equations. The final fitted equation becomes p of x minus 2181.5 plus 352.7x. But since the dataset behaves more like a cubic function, the linear fit is not perfect. Orthogonal polynomial approximation. In normal least square fitting, higher degree polynomials can make the calculations unstable because the matrices becomes ill-conditioned. To solve that problem, we use orthogonal polynomials like Lagrange polynomials. The important idea behind the method is each polynomial basis function is mathematically independent from the others over a specific interval. That's why orthogonal means the formula are read as p0 of x equals 1, p1 of x equals x, p2 of x equals 3x squared minus 1 divided by 2. And the orthogonality condition is integral from minus 1 to 1 of pm into pn dx equals 0 for m not equal to n. Because of this property, calculations become more stable and accurate, especially for higher degree approximations. At the bottom, the Python code uses Lagrange fitting to approximate the dataset and evaluate f of 9. Now we move to solving ordinary differential equations numerically. The equation given is dy by dx equals x plus y, with y of 0 equals 1. The goal is to estimate future values of y step by step. We will solve this using Euler's method, Runge-Kutta fourth order, Picard's method, and Taylor series method. Euler's method. First is Euler's method, which is the simplest numerical ODE solver. The idea is very straightforward. We move step by step using the slope of the tangent line. The formula is pronounced as yn plus 1 equals yn plus h into f of xn comma yn. Here h is the step size, so basically current value plus step size times slope gives the next value. Using h equals 0.5, we get y of 0.5 equals 1.5 and y of 1 equals 2.5. But the exact answer is about 3.4366. So Euler's method has noticeable error because it is only first order accurate. Still, it is very simple and useful for understanding the basis of numerical ODE solving. Runge-Kutta fourth order method. So this is one of the most widely used numerical method because it gives very high accuracy. Unlike Euler's method, Runge-Kutta fourth order does not use just one slope. Instead, it calculates four slopes k1, k2, k3, and k4 at different positions inside the interval. Then it combines them using a weighted average. The final update formula is pronounced as yn plus 1 equal yn plus k1 plus 2k2 plus 2k3 plus k4 divided by 6. This makes the approximation much more accurate. For example, RK4 gives y of 1 approximately equal to 3.4325, which is extremely close to the exact value of 4.366. So RK4 achieves very high accuracy even with larger step sizes. Picard's method. This method works using repeated integration. We start with an initial approximation, then substitute it back into the equation repeatedly to get better approximations. The formula is pronounced as yn plus 1 of x equals 1 plus integral from 0 to x to t plus yn of t dt. So each iteration improves the previous solution. One interesting thing is that Picard's method gradually builds the Taylor series of the exact solution. As the iteration increases, the approximation converges towards the exact answer. That is, here we get 1.7943 with the error of approximately 0.003. Taylor series method. This method expands the solution as a Taylor series around the initial points. The formula is read as y of x plus h equals y of x plus h, y dash plus h squared by 2 factorial, y double dash plus h divided cubed by 3 factorial, y triple dash, and so on. To use this method, we repeatedly differentiate the original differential equation to find higher order derivatives. Then we substitute them into the Taylor expansion. The more terms we include, the more accurate the solution becomes. For example, higher order Taylor expansion gives values extremely close to the exact solution. So that completes the entire assignment. We covered root finding methods, interpolation, numerical differentiation, numerical integration, linear equation solvers, approximation techniques, and numerical methods of differential equation. We also compared convergence speed, computational complexity, and accuracy of different methods. Among all methods, Newton-Raphson showed very fast convergence. RK4 provided extremely accurate ODE solution, and Gauss Quadrature demonstrates highly efficient integration. Okay, thank you for watching.